Hello, my name is Mark Ashenhust, and this is my DAT 301 Exploring Data in Python and R Project 1 on multivariate computer hardware, which was my chosen data set. The information for this was found at this link, the archive ICS, and I analyze multiple sets of data. The data values, the columns that were given in this data frame were vendors, models, model name, machine cycle time, minimum main memory, maximum main memory, cache memory, minimum channels and maximum channels, published relative performance, and estimated relative performance. Of these, the notable ones I chose were vendor model name, machine cycle time, minimum maximum memory, cache memory, and estimated relative performance. And the estimated relative performance is a great metric to see whether or not a certain vendor has really good performance, or if having a higher maximum main memory will increase the estimated relative performance of that hardware device. Moving on from here, I did a simple load in the data and print out a summary of the data. So we just have a simple summary here of each column. So we have the models, we have the cycle times, the min memory, we have the mean, maximums, minimums. We have everything listed right here, which is really valuable information when we're analyzing certain columns further, certain like machine cycle time. Moving on from that, we go into my first analysis. First analysis is simple, and we just want to look at how many parts there are per vendor. So I took just the table data, the vendors, and got each individual vendor, just individual unique vendor names, because there are a lot more vendors listed than there are total vendors, because one vendor could have multiple parts, one vendor being IBM. And we'll see IBM here had many hardware parts. The second part of that is to show the values individually. And as we can see here, the number of hardware parts is the y-axis, and then the hardware vendors are on the x-axis listed there. We can see that IBM has the most, and it's actually equivalent to 30. IBM has 30 hardware parts in this data set. And some of them have very little, like one. Advisor has one, 4-phase has one, Microdata has one, Stratus has one. So this helps us gauge how many parts are there per vendor. And then we move on to my second analysis here, and that is on the machine cycle times. The cycle times are given in nanoseconds, and they are important to note the speed of this piece of hardware. And now speed, what we want is something to be quicker. So the values we want are going to be from least to greatest, because actually the smallest value is the most valuable, the quickest, right? So the first thing I did there is I wanted to just find the top 5 quickest. So I sorted it from least to greatest, and then I printed out the vendor, the model name of that hardware part, and its machine cycle time. As we can see that out of 5, there's only 2 vendors that are listed here, with IBM taking the top 2, and then AMD AHL taking the next 3. Which is important to note that we see IBM has the most devices, 30 devices, and they have the top 2 machine cycle times out of the whole set of data. Going next, I put this I visualized this, and we can see all pieces of hardware, all of them just combined together. We can see the lowest machine cycle times to the quickest machine cycle times, just going straight up. So we can see that lots of the pieces of hardware are actually close to the bottom. So lots of them are quick. and by the 150, that's an index, so that'll be the 150th piece of hardware that's in this list. By about the 150th or 100, maybe 25, somewhere in that middle there, that's when it starts going up. So there's at least about 100 plus pieces of hardware that are all around 17 nanoseconds, 23-ish. And then it kind of grows up into the 50s, 100s, and then past 150, it just skyrockets to 500 nanoseconds to 1,000 nanoseconds, which would just go way slower. It'd be we're getting into microseconds now, so 1,000 would be 1 microsecond, pretty slow. And then we can move into my explanation of this. The data clues us into why IBM has the most hardware parts, because the top two are IBM's. And then we can see that the range goes from about 17 nanoseconds to 1,500, so 1.5 microseconds. Now we move into the third analysis. My third analysis here is the comparison of the min and the max main memories. So that goes mmin and mmax that we saw in the column values that were given. So from here, we could see the range of the minimum of the minimum. So that would be like the lowest we can get. And then the maximum of the maximum memory values is going to be the highest we can get. So moving on there, we get into some code and where we compare these minimums and maximums on the same chart. So the blue we have here is going to be the maximum memories, and the orange is going to be the minimum memories. We can see, though, that the minimum and maximum start at the same place. That means there is a hardware device where their minimum memory value is equal to some other device's maximum memory value. That's really interesting to show disparity, because that means either one device is really bad or one is really good, right? We have one device with a really low, or we have a device with a maximum that's so small that you would have a special use for, maybe. After that, we can see the minimum value. The minimum of the minimum is 64 kilobits, and the maximum of the maximum is 64,000 kilobits, which is difference by a factor of 1,000. Here, I wanted to see the lowest 5 memories and the highest 5. So we can see those listed here with the vendor, the model, and the minimum memory. We can see there's only one that has a minimum of 64. And then we have the top 4 of the highest have high memory capacities of 64,000 kilobits, 64 megabits. And that's another important thing to know here, is that AMD AHL is popping up again, which we saw were the high on the machine cycle times. They were 3, 4, and 5. So now it's making AMD AHL look like a better group, because they have higher memory capacities and they're in the top 5 quickest. So you may not need the most fast processor or hardware piece of hardware, but you might need higher memory and fast. So and after this, we move into my fourth analysis, which does just the memory values for IBM hardware. And I wanted to do this because I like IBM. I've known that company for a while. I've heard their name just everywhere and seen their parts, had their hardware before. And they were the most popular out of this whole group. There were 30 IBM devices, so it would be better to analyze them. As we can see, there are 32 IBM hardware devices. The minimum memory is 96 kilobits, and the maximum is 32,000 kilobits. From here, I took each individual model from IBM and compared their minimum to maximum. So we can see that the 3081 and the 3081D both have a stable minimum capacity, just somewhere, they're pretty high, and then a high maximum. And that's where we get that high 32,000 kilobits is going to be these two devices, the 3081D and 3083B. And we can see that the largest range looks like it's 3083B. So from here, we can find the best memory capacities between all of the IBM hardware. Now, a question from this and something you might be interested in, though, is why just IBM hardware? Why don't we take a look at all the other pieces of hardware that you can find in this data set from all these vendors, right? 30 vendors. So that is the next thing I did is I did a fifth analysis where I compared the memory values, the maximum memory values for each vendor. So there are 30 graphs right here. It's a 5x6, 5 rows, 6 columns. And it just compares the maximum memory values. So what it does is say IBM has 30 devices. We can see that here going out. Each value, it plots in order, it plots the minimum of the maximum memory values, and then it prints the maximum of the maximum memory value to the maximum of the maximum memory values. So we can see the range for each different vendor of their maximum memory values. We can see IBM goes 0 all the way up here. The top here is going to be at 64 kilobits or 64 megabits, because as we saw with AMD AHL, they did have 2 devices, and another one here, Sperry had, I believe, 3 devices that could reach 64 megabits for their maximum memory. So by this all being topped at 64 megabits, 64,000 kilobits, we can see that some of these values get very low. They don't get all the way up there. So say Burroughs or CRD doesn't really move up much, but it's very low. Because if we saw a line for CRD that was all the way up here that was straight, that means all of their values, they're probably about 7 devices, are all high. They're all like 64,000 kilobits for their maximum memory. But looking at it, we can see that they're pretty low for most. It really caps off with Sperry and AMD AHL, and then the rest don't really get close to that 64,000 kilobits. After this, here's the explanation, which stop here for a moment, but I just explained all that. Next, I have my 6th analysis. So what we've been doing previously, the past 2 analyses, were on just memory, regular memory. Now, cache memory is something different. Cache memory is expensive, quick, and it's usually what you're going to find in RAM, your random access memory, in your computer. And cache memory is expensive because it's very quick and very useful. If you're trying to build a computer and you want to put 64 gigabytes of RAM in your computer, that's going to be a lot more expensive than if you wanted to put 4, or usually in the case now it's 8. 8 is about what's becoming the average-ish for lots of programs. They require about 8 gigabytes of RAM. And now the cache memory in these small devices might not need to be that high. It's probably not going to need to be that large because they're going to be small devices. So what I wanted to do here is compare the highest and the lowest cache. So what I'm doing in this analysis really is taking the machine cycle times and the cache memories in a rank. So from 1 through 5, I take the top machine cycle time device, and I take the top cache memory, and I look and compare. And what I want to do is I just want to see if any of them match. I want to see if cache memory has an influence on the machine cycle time. Because if they all lined up, all the cache memories, all the highest cache memories had all the best machine cycle times, then we'd see a correlation. We would kind of know that cache memory has an influence on the machine cycle time. But looking at this, if we look at 1, 2, 3, 4, and 5, we see not a single one of these matches up. So what that tells me is that your cache memory, the size of your cache memory, does not have a significant influence on your machine cycle time of that vendor model, which is very interesting. So that was a theory that was debunked. And now my 7th analysis is another theory dealing with cache sizes. But I wanted to compare the cache size to the relative performance of that device, which is ERP, the estimated relative performance. That was the last column when we began. I told you all the data values we would be going through. So we have ERP and our cache size. So to see if they had a significant influence on it, we want when one is high, the other is high. When one is low, the other is low. They're going to be proportional. So if I have a really low cache size, I want a low estimated relative performance to prove that they're proportional, that cache size does have an influence on relative performance. Because relative performance, you need cache size to get a relative performance. Therefore, you can't say that it has a really good performance and then cache size. It's a one-way comparison. It goes from cache size to performance. And to do this rather than text, what I did with the last one, I did it with a graph, a bar chart, where I took IBM device models, went back to IBM, and I took their cache sizes and the estimated relative performance. And what I saw here was that though the values are low, right, like some of these cache sizes are really small, they're not even there, you can see that when the cache size goes up, the estimated relative performance of the device goes up too. So that tells me that it is proportional, that there is, when you do have a larger cache size, that your estimated relative performance of the device does increase. Now, that's not to say it is completely proportional, because as we can see, the cache sizes and all three of these are the same. However, they all have 3 different estimated relative performance. So that means there's other variables in there. There's other parts of this data that may make it better, may make it worse. But the fact that all 3 of these are high and the ERP all went up shows me that they are somewhat proportional, that there is some influence that cache size is going to have on our visualization, on our ERP. So that is all the analyses I did. In this document, there were 30 different vendors compared, and I wrote up short closing statements for each analysis. In the first one, we saw how many different hardware devices came from different vendors. This was basically just taking all of finding out how many vendors there were in the data set, because we had more than 300 plus pieces of hardware, but we only had 30 vendors because there were multiple duplicates. Like IBM had 32 devices. There was no reason to count IBM 32 times. The second analysis was comparing machine cycle times, and we got to see the range of machine cycle times from the shortest cycle time to the largest cycle time, and we could look at the specific pieces of hardware that were at the very bottom and the ones that were at the very top, which could definitely clue us in or let us know the quality of that hardware that we're going to be using or that you're going to be purchasing. The third analysis was the minimum and maximum memory sizes on the devices, which is important to know because you may have certain applications that need a large space of memory to do what you need to do. And also, there may be a hardware device that doesn't need a lot of memory to run, or really needs like no memory to run, very, very minimal. And that could be below one of the minimums we have, and that wouldn't work out either. Our fourth analysis was just comparing the IBM memory sizes, and we got to see which IBM devices had more memory than the others. So this was to say that we went into a store, we saw all these vendors, these 30 vendors, and we liked IBM. We wanted the IBM vendor. So what we did is we now compare IBM's memory sizes. So out of this, we were not seeing every vendor, we were seeing which IBM device had the best memory sizes or had a memory size that fit our need. Now, the fifth analysis was very similar to the fourth. However, we didn't use any machine names. We didn't really need any hardware names per vendor, right? We didn't need all 32 models for IBM, because the point of this was not to see which device that we wanted to choose that fit our requirements. We wanted to look at every single vendor in all of their hardware devices and compare their maximum memories. We wanted to see if this certain vendor had a maximum with a very large range or a small range that was very high. There were some there that had a small range that barely moved. It was very linear, just very small fraction slope. That means that their memory sizes aren't very variable. They're very small and they don't change. So even if you get their highest end memory device, it's still not going to be that much compared to AMD AHL, which could give you 64 megabits of memory. The sixth analysis now compared cache memory, something else that I described, and I wanted to compare this one to the machine cycle times. I wanted to see if there was a correlation between having more cache memory and machine cycle time, to see if having more cache memory gave you a smaller machine cycle time. Does it really have a big influence on the performance of that device? Turns out that was wrong. There was a bad correlation there. And none of the top 5 really showed that having a larger cache memory gave you a better machine cycle time. Which was very interesting to me to see, because I definitely thought that would increase it. However, with our 7th analysis, we saw that it did have an influence. It had a good correlation with ERP, estimated relative performance. We saw that having a higher cache memory size for IBM, at least, right? This was just with IBM, their 32 devices. Having a higher cache memory size gave better estimated relative performance for IBM devices. Also, the correlation was not exact. So that means that there were other factors, there were other things that were going on in this analysis, there were other factors in these hardware devices that increased the estimated relative performance. So that doesn't mean all you need is a good cache size to have good relative performance. It means having a good cache size will increase your estimated relative performance, or should increase your estimated relative performance. It's a good metric to use. And then the last statement I'm going to say here is, I know lots of the memory sizes are very small. This data set was taken somewhere in the 80s, 70s. And at that time, having these memory sizes of 64,000 kilobits for the max is pretty high. That's good. I know there's lots of, you can go out and buy a hard drive at Best Buy now for $80 and probably get 4 terabytes of information, which is a lot more than 64,000 kilobits. Lot more. But that's for hard data storage. If we went to cache memory, it's still the same story, where the minimum you would see for RAM in a computer now is almost probably about 4 gigabytes, which is 4 billion bytes, which is 4 billion times 8, which is 32 billion, and which would be 32 billion bits. And then you have 64 kilobits, or 64,000 kilobits, 64 megabits. So we have 32 billion versus 32 million. It's a very big jump between 2022 and the 80s and 70s in memory. So if those values still seem really low to you, keep in mind the change in time. And that is all. That is the end for this project on multivariate hardware. Thank you.